Yes, awesome. Okay, welcome to the next session of Hot Pets, where we've got two interesting discussions, and I think we've mostly finished filling in, so I'm going to let Sandra take it from here and take it away.
Thanks for the introduction. Can everyone hear me? Yeah? All good. Okay, cool. Hi, everyone. Today I'm going to talk about traffic analysis of encrypted DNS traffic. And this is a work in progress that I'm currently doing with Mark, Narceo, and Carmela. So as we all know, almost every connection on the internet is preceded by a DNS lookup. So let's say we have a client, and the client wants to find out what the IP address is for a particular domain name. The client sends this domain name as a DNS query to a recursive resolver. The recursive resolver contacts a number of authoritative name servers which hold databases of DNS domain names to IP address mappings till it receives the correct answer for the client's query, and it sends us back as a response to the client. Once the client receives the IP address, it establishes a connection with the destination host, and it can exchange data such as HTTP requests and responses. So in this work, we are going to focus on the link between the client and the recursive resolver. So the main issue with DNS is that the DNS queries and responses are unencrypted, which means that they're vulnerable to eavesdropping and tampering. So this gives eavesdroppers an extra channel in addition to the link between the clients and the destination host, on which they can learn more about the activities performed by a client or an end user, such as the browsing history. Another thing is that DNS is used to implement censorship. So parties such as ISPs can look at DNS queries that are performed by clients and can censor based on the queries as well. So if we look at the big picture right now, the idea is to encrypt the connection between the clients and the destination hosts using protocols such as TLS. So the next step would be to encrypt the connection between the client and the recursive resolver. And we already have certain big players such as Google and Cloudflare that have released solutions using DNS over HTTPS to encrypt the DNS traffic between the client and the recursive resolver. So DNS over HTTPS is a relatively new protocol where the idea is to establish an HTTPS connection between the client and the recursive resolver and use that to exchange queries and responses. So what we were interested in studying, and we found out that so far it's not been done, is if the DNS traffic is encrypted, can we still do traffic analysis on the encrypted DNS traffic to find out which domain name is being queried by a particular client? So the question may arise as to why we should even do traffic analysis of DNS traffic in the first place. So let's say that the DNS traffic is encrypted, and then the subsequent connection between the client and the destination host is also encrypted using protocols such as TLS. You still have the IP address of the destination from which you could potentially learn the domain name that the client is interested in visiting. While this may have been true before, now you have the virtual hosts where multiple domain names could reside on the same IP address. So it becomes harder for an eavesdropper to figure out which domain name a client is interested in visiting. Another thing is that you have content delivery networks, or CDNs, which host resources, and often you might end up getting the domain name of the CDN, which is not very interesting from an eavesdropper's point of view. So in order to do our analysis, what we did is we took a bunch of Raspberry Pis and we set them up as clients that can contact resolvers which implement DNS over HTTPS, and these are Google and Cloudflare's resolvers. We considered a relatively simple scenario where there is no client-side caching of DNS responses as a starting experiment. And we ran TCP dump on the clients at the moment to collect traces. Note that even though we are running TCP dump on the client, this kind of analysis can be done on any eavesdropper that is on the link between the client and the recursive resolver. And at the moment, we are looking at the packet sizes, the timing, and the ordering, which indicates the directionality of the packets as features. We also looked at the header information in the TLS headers, but we didn't find anything interesting in our, so we're not going to include TLS header information in our analysis. So when a client contacts a hostname, so let's say that you have a browsing session and you want to visit reddit.com, so you sent an HTTPS request to Reddit servers, and then you get a response. But the thing is that the Reddit's web page might include a lot of other resources as well, such as image files, ads, and static files. And these could be residing on other domain names. So there could be DNS queries that are associated with these domain names as well. And we are interested in capturing all the DNS data that is associated with a particular browsing session for a web page. However, in our first set of experiments, which we call as single query experiments, we are interested only in looking at the DNS query and response pair for a particular domain name. And the reason that we conduct these single query experiments is that we want to see if there's a quick way of identifying domain names based on just the first query and response pair. This could have an impact on censorship, where the censoring party might want to quickly determine whether a website has to be censored or not. And also it gives an upper bound on the privacy that can be obtained from DNS over HTTPS solutions. So in order to do the single query experiments, we use Google's and Cloudflare's DNS over HTTPS API. So they have an API where you can send the query and then you get back the response. So we collect the network traces associated with performing this particular API call. So for our first set of experiments, we wanted to gather traces associated with querying a large set of web pages. So we looked at Alexa's top million web page list. So since these experiments are still running, here I'm going to show the results for about 450,000 pages that we have at the moment. And we are considering the packet size information for our analysis. And we look at the anonymity set size. And here I define anonymity set size as the number of web pages with the same query and response size tuples. So we look at the count for each anonymity set size values. And the plot here shows the cumulative distribution of these counts. And the main point that we want to highlight from this plot is that the smaller anonymity set sizes actually dominate our results. And even when you increase the number of web pages that you have, you still see that rather than having larger anonymity set sizes, you have an increase in the number of small anonymity sets. And here's a view for the smaller anonymity set sizes. So what we see is that 1.7% of the web pages that we analyzed have an anonymity set size equal to 1, which means that they have unique query and response size tuples. So you can actually uniquely identify these web pages just based on the packet sizes. And if you look at the list of the web pages that we got, these include pages related to healthcare data. For example, there was a page which was for cancer screening. We had financial web pages. There was a page where the idea was to calculate your credit score. And then there are a lot of pornographic web pages as well, which could possibly come under censorship as well. After this, what we were interested in analyzing was whether these DNS query response sizes that we get actually remain the same or they change within a very short period of time. So what we did was we took the subset of the web pages with anonymity set size equal to 1, and we ran the same experiment multiple times within a short span of time. And then we looked at the sizes of the queries and the responses. So here I'm just showing some sample plots just to show the kind of trends that we observe. So we categorize the trends in the sizes into 3. So dominant category means that we see only one particular size value over all our experimental runs. And in a bimodal category, we see that there are two different packet sizes that we observe. And then we have the multimodal category where we can see multiple size values. So what we see is that as expected in the sent packet sizes, you do not see any variation. They belong to the dominant category because you're querying for the same web page over and over again. However, we see that in the received packet sizes, even though majority of the sizes belong in the dominant category, you do see differences. So you see the bimodal and the multimodal values. And then we looked at the responses in the API from this. So these experiments were conducted with Google's DNS over HTTPS API. So when we looked at the responses, we found out that there is a comments field in this API section. And this comments field includes some details such as which authoritative name server actually served the DNS response. So this comments field is not necessarily present in all of the DNS responses, and the name server that responded can also vary in the responses, and these lead to differences in the received packet sizes as well. Then we decided to see how the DNS data varies over a longer period of time. So we took the top, middle, and the bottom 500 web pages, and we performed the same experiment, but over about 39 days. And we looked at the, how many web pages actually show some changes in the packet sizes. And we found out that, so we categorized the changes into small changes, which could be changes in an IP address, for example, and large changes which could have been caused by the presence or the absence of the comments field. And we found out, as expected, that there were web pages that show the variance over several days. In the initial days of the experiment, we actually found some large fluctuations. So there were a large number of web pages that showed a change greater than 10 bytes here. And we are not really sure as to why these fluctuations were caused. Maybe there was some error message which could have contributed to differences in the packet sizes. So we are still running the experiment to see if this behavior occurs again. So as I mentioned before, in our single query experiments, we were looking only at the first query and response. But in the next set, which we call browsing experiments, we look at all the data that are associated with a particular browsing session. So what we did was we set up Cloudflare's DNS over HTTPS client on the Raspberry Pi, and we used Selenium, which is a browser automation testing tool, with a Chrome driver to replicate a browsing scenario where the client visits a particular page. And we did the same sort of analysis where we looked at the sequences of the sent and the received packet sizes for all the DNS data. So for this, I have a much smaller set of web pages because these experiments are relatively recent and they are also more time consuming. And what we found out was that 98.9% of the web pages actually have unique tuples and can be individually identified. And the largest anonymity set size is only 22. We have also started trying to classify the web pages based on size and ordering information. So right now, we looked at a hidden Markov model where we tried to classify sequences of sizes for a particular web page. So we created models for each web page, and then we have a test size sequence, and we try to see what is the probability that that sequence belongs to a particular web page's model. So at the moment, I have cross-validation results that show average accuracy for about 1,500 web pages. And we are also looking at the top N accuracy, which means that the correct result is present in the top 10 guesses of the classifier. So at the moment, our top one is about 29% accuracy, and the top 10 is 47%, which is not bad, but it's not amazing either. And I'll come back to that. So we look at the longitudinal study, and we see that this is over about 11 days, and we see there are large fluctuations in the number of packets that are being sent and received. and they follow a multi or a binomial distribution. And we are studying in more detail as to how there are variations in the number of packets as well as the size between web pages, as well as how the variations occur for a single web page. And these factors could have an impact on classification. We are also considering other classification models outside of the HMM and seeing whether we can extract higher level features than individual size sequences. We have also started a few other experiments. The first one is to study the impact of the client. So we vary the location of the client and we see if that has an influence on the DNS data. And we also want to see if data that is trained on a particular location can be used on test data from another location. We also want to study the difference in DNS data between the mobile and the desktop environment, because different websites are optimized for mobile, so it could be different domain names. And we also want to study more realistic scenarios where we consider client-side and resolver-side caching. And finally, we want to compare our results with the DNS over TLS protocol, which is another protocol that also aims to provide encrypted DNS. And Cloudflare has released a DNS over Tor protocol recently, so we'd be interested in studying that further. And finally, we want to look into designing better countermeasures, which might include removing unnecessary data from the APIs, or maybe padding-based measures as well. And I guess the final question is, even if we do all these measures for DNS privacy, whether the rest of the ecosystem is ready for getting full privacy for the user. There are recently some improvements in TLS, for example, but it takes time, and I guess we'll have to wait and see. Thank you.
Okay. So we've got time for some questions and comments and discussion, and I'm going to hand it to Ian first, and then Tarek will go from there. Ian first.
Aha. Okay. So, two things. One, so on slide, I think 8 it was, you pointed out, obviously the observer can see the IP address just from the TLS, but they can also see the host name because it's in SNI until such time as ESNI rolls out, hopefully with 1.3, but maybe not even.
Yes.
So, I mean, it's important to block the leakage at every place, but blocking it, like right now, the easy attack is the attacker just looks at the SNI, but it's of course important to stave off this information leak as well. So that's great. The question for countermeasures. So, so what do you think? Can you just do a simple padding scheme on at least the single queries? So I know your colleague Brian Ford just has a new paper with this spiffy new padding scheme that has lower overhead, and you might want to look at that. You probably have already, but that's just for the single query. So what do you think you could do? Like some websites will load 20 DNS names and some will only load 1 or 2.
Yep.
How do you think you should protect against?
So there were two things that we were considering. The first one is, as I mentioned, currently the responses in the API for a particular DNS query. So we want to know what parts of a DNS response are, first of all, unnecessary and which do not actually contribute to the functionality of DNS, and maybe think about removing the unnecessary parts and seeing if that leads to some kind of improvements. The second one is, like you mentioned, padding-based countermeasures. So in, I think, traditional website fingerprinting techniques, you do have padding-based countermeasures, and there are some works that show that they are not super effective because certain trends in the traffic, such as the burst behavior, for example, is still known. The thing is that DNS traffic could follow a little different pattern from normal website accesses, so we'd want to first implement padding-based countermeasures and see if it is sort of, it works for DNS as well. I think Karna.
And there is.
Tarek's got two.
All right.
I'm gonna answer to Ian. So also Cloudflare, they have a pipeline of countermeasures. Sorry, Cloudflare also is thinking about putting more things on the encrypted tunnel, and one of the things they are thinking about is including the DNS request when you talk to the website, so that they also serve you the DNS domain, so everything would go on the HTTPS instead of going back to the resolver. So there are some things coming there in the pipeline, which would do the traffic analysis when they come there. But that's an option, for instance, to try to avoid all of this coming and going, is instead of going back to the DNS once you got the first domain, then that domain can tell you the IPs of all of the rest of the stuff that they're serving to you.
Okay, so Longcat of the Internet asks, if one visits one website, multiple requests to third parties will happen, likely. Their domains have to be resolved too. How about size of the anonymity set when paying attention to those combinations of DNS requests?
Sorry, I didn't get
So what they're saying is when you go to one domain, you're actually going to request third-party website, which also have to be resolved.
Yes.
So what's the effect of that on the anonymity set?
So we haven't specifically, so here I show the anonymity set, but we haven't specifically studied what is the difference between when you visit some kind of third-party resources and so. So right now we have implemented some logging to see what requests are being made, and that's something that we are planning to study further, but we haven't done that analysis yet.
Okay, another question from the internet. The DNS protocol itself asks, question, did you measure the effectiveness impact of DNS padding, RFC 7830, on your classifiers? Does it have a significant impact?
No, because we just started the classifier study. So first we have to have a good classifier that has better accuracy, and then after that we look at the padding measures.
Cool.
Hi. Probably a stupid question, but why did you look at DNS over HTTPS in preference to DNSSEC? And if that's not a stupid question, how would the results differ for DNSSEC?
So DNSSEC is for authentication and not encryption of the DNS. Yeah. But just to further elaborate, there are other protocols such as DNS over TLS, and then there's also DNS Crypt, which looks mainly at authentication but also does encryption. The reason that we are specifically focusing on DNS over HTTPS is because you have companies such as Google and Cloudflare that have released these solutions, so it looks like it might be gaining more widespread adoption at the moment.
So DNS is back with another question. So if you make DNS resolvers harder to identify, how much better would this make the traffic analysis race in favor of the user? So if you make the resolver harder to identify, the DNS resolver,
okay,
right? How much would this help in the traffic analysis arms race?
To identifying the resolver, you mean?
Yeah.
I guess, okay, I mean, like, I suppose, I'm not sure I understand the question perfectly, but I guess for Cloudflare, they have like a very distinctive IP, so it's easier to identify that requests are going to Cloudflare's IP, I guess, versus something like Google where the IP changes. Yeah, I guess it becomes easier to get the traffic associated with a particular IP. You can still see from the SNI, as he says, which resolver is currently being accessed from the TLS session with the resolver, but if the SNI is encrypted, then I guess the IP does kind of help identify the traffic going to the resolver.
Cool. I'll sneak in a question while I'm handing the microphone to Aaron. Yeah. So one of the challenges that I see here, Cloudflare is the central service for a lot of things, and they get to learn a lot.
Yes.
So encrypting the connection to Cloudflare when Cloudflare still gets to learn everything, and same with Google, seems like it might not be solving the biggest part of the problem. The biggest part of the problem is that the whole DNS infrastructure is way more centralized than people would like, and protecting the transmission to the place that spies on you is not the whole problem.
Yeah, I totally agree. I guess the question is whether you would prefer your ISP's DNS or a big corporation's DNS to reply to your DNS queries. So Cloudflare tries to portray themselves also as a trusted resolver. So they say that they're going to delete the DNS records or any kind of identifying information within 24 hours, and that they will have regular audits of the data to make sure that they're following the right procedures. But yeah, I mean, it's just a few big players at the moment that are...
Wouldn't it be cool to use technology to enforce the security?
So I have a question. This especially pertains to the single query case. It seemed like you were looking in a closed world. You had like 100,000 and then 500,000, and you had anonymity set sizes. That's within that set of 100,000 or 500,000 sites,
yes,
right?
That's right. Yeah.
Okay, so I was wondering if you could comment on the fact that there are way more than 500,000 domain names on the internet. I mean,
yes.
Maybe millions, I don't know, billions. So what can you really say, what can you really conclude about, especially a single query, the packet sizes, do you think?
Yeah, so I think I forgot to mention it in the talk, but we were also thinking of expanding the study to include an open world scenario where we would try to classify websites that are outside the ones that we've trained on as just unknown. I guess for the closed world, it might be useful in cases like censorship if you're looking at a specific set of websites and you're just looking at traffic analysis and you want to identify only those. But yeah, with an open world scenario, I think it becomes much harder.
How feasible would it be to do this test on all the domain names? It is a finite size. It's not that big.
Yeah.
Have you thought about that?
Yeah, so you mean the single query experiment? Because the browsing experiments will take a really long time, but the single query experiments, I think, I guess it depends on how many Raspberry Pis I have finally.
Okay, let's have the next person come and set up, and there's time for one more question while the next person is coming and setting up. You're stretching, Harry. Okay, sounds good. Paul's got one.
So you talked about padding and stuff, and then you also mentioned Cloudflare's DNS over Tor, and subject to Roger's very valid observation about Cloudflare. I mean, Tor inherently does a degree of padding. Do you think that in general, I don't know how much of this like extra stuff they've been putting in these, but for single query, not the sequences, would that by itself be enough padding that they're all going to look the same for the single query DNS lookups? So Cloudflare has DNS over Tor, right? Tor pads to uniform size. So in a single lookup case, I don't actually know how big the DNS. I'm just repeating to her.
I think that we will go to anonymity set of 1 or 2. I think some of them are too long.
Anonymity set of 1 or 2. We're going to let this one go offline rather than it was the short question that was. Thank you again. And next up, we've got Eric talking about browser level tracking.